Hello, I'm Paul DeZino from AGR. I'm here today to give you a quick glance into AGR Academy's PET101 training class. We developed this for newcomers into the PET industry and also for seasoned engineers who are moving in from another industry into PET101. This gives a very comprehensive background into the entire PET production process. For this session, we're going to give you a brief view into the first of the presentations for PET 101, and this is on material science. So what is PET? It stands for polyethylene terephthalate, and terephthalate is an acid and it's combined with ethylene glycol. It's one of the polyester family of polymers. PET is a macromolecule, very long, complex molecular strain, and anybody who's in the industry is familiar with homopolymers and copolymers. When PET bottles were first made, they were made with homopolymers. It had limitations in its overall strength and how much you could stretch it. Copolymer adds catalysts into that PET molecule which make it stronger. Anybody who is familiar with PET bottles back in the 80s when we started producing them, you'd see these 2-liter bottles with a high density polyethylene base cap. That's because the monopolymer wasn't strong enough to be blown into the petaloid base feet that we see today. Once we developed copolymers, which increased the strength of the material, that's when we were able to move away from that separate process, adding this injection molded high density cap and hot gluing it to the bottle to what we see now as petaloid feet. Another key part of the overall process is looking at the material, the PET resin. A key factor in that is what's its intrinsic viscosity. That's its molecular weight. The higher the molecular weight, the longer and more complex the PET molecules are, the molecule strings. So, for instance, flat water uses a relatively lower IV of around 0.76, whereas CSD bottles uses a more complex molecule at a 0.84 IV. It needs that additional molecular weight and the strength in that complex molecule to be able to stand up, one, to the pressure that's going to be applied internally to the container, and two, because of the extreme stretch that we're asking the preform and the plastic to go through, forming those petaloid base feet. Why don't you use 0.84 on all containers? Well, that's because the higher the IV, the more expensive the material is. So we use only the IV that's required for the particular type of container that's being produced. Some other key factors we look at are, there's terms in PET called glass transition, crystalline transition, and melting transition. So starting with the resin that you purchase that we're going to melt and injection mold into a preform, that melt transition temperature is above 240 degrees C. That's the temperature you need to get the PET to for it to melt and be able to then be extruded into the series of molds that are all made at once, 96, 144. So you have to get the PET above that melt temperature. Once that preform is cooled, it gets to the production site where you're going to be producing the bottles. Then we start looking at what the glass transition temperature is, and we also pay attention to the crystalline temperature. The glass transition is between about 95 degrees C and about 140. And we typically like to be in the 110, 115, 100 degree range, and that's where the plastic becomes elastic. And it becomes elastic enough that we can blow it into the mold and form the container. When we start getting above about 140 degrees C, we start generating heat-induced crystalline structure. There's certain processes we want that to happen. For things like water bottles and CSD bottles, we don't want that to happen. So we operate entirely in that 120, 30 degree temperature range. When we start talking about heat set containers, we'll get into the crystalline transition where we're going to cause it to grow, increase crystalline structure. So why that's important is There's two ways we generate strength in the container. One is through mechanical stretching, where that mechanical stretching in a biaxial orientation, vertically and horizontally, generates strain, and that strain is basically equates to a crystalline structure, so percent of crystallinity. In a preform state, it's got a very low crystalline structure, about 4 to 6%. Once we go through the mechanical stretching on a water bottle or a CSD bottle, we like to get somewhere around 20 to 25% crystalline structure. That's why you can have a very light water bottle, very lightweight water bottle, but it still has rigidity to it. That's because through the proper stretching process in the blow molder, we're generating that mechanically induced strain and that crystalline structure. For things like heat set bottles, we're going to increase that by adding additional heat through having the mold heated as opposed to the mold chilled or cooled for water bottles and CSD bottles. And that causes additional crystalline structure to grow. So we get somewhere between 25 and 40% crystalline structure. When you look at crystallized PET, so when sports drink bottles were first being produced, you would see bottles with a 38 or 43 millimeter finish that was white. That's because the processes weren't developed well enough in the blow molders to have stability in that finish. And so what they did was they superheated it to somewhere between 50 and 55 degrees percent crystalline structure, so it actually turned white. So they were making it very rigid and heat resistant. So being able to control that crystalline structure is a critical part of the blowing process, and understanding how that relates to the glass transition temperature and the thermally induced temperature is very important. So on this slide, we're looking at why is crystallinity important. And we're looking on the horizontal axis as the temperature that we're heating it to, and on the vertical axis, the degree of mechanically and then thermally induced crystalline structure. So we have to get up to about 85 or 90 degrees C for the preform to soften enough so we can stretch it. And as we're stretching that, when we hit the full horizontal and vertical stretch point of the container, when it's a properly designed preform and bottle and process, you're going to get the maximum amount of strain-induced or mechanically induced crystalline structure. Above the dotted line at 30% crystallinity, you're seeing additional crystallinity, and that's thermally induced. It's called spherolytically induced. As we retain more heat in the PET from little nucleuses within the PET, it'll start growing this crystalline structure, which gives us the added strength for a heat set container where you're doing hot fill. So things like Gatorade, some food products, where in order to keep them from spoiling, you have to go through a hot fill process. Without that additional thermally induced crystalline structure, that PET bottle will just shrink, trying to get back to its preform state. When you apply this thermally induced, the additional crystalline structure through thermally induced, then that bottle will retain its shape and be able to withstand the high heat from that hot fill process. So you get the vertical stretching and aligning of the molecules through the stretch rod that's going through the preform and then holding the bottom of that preform at the bottom of the mold. You get the horizontally induced strain in the blowing process as that preform expands into the mold walls. So that's how you get horizontal and vertical strain-induced crystalline structure in the container. There's a lot of things that affect that. The temperature that you're initially taking the preform to, the type of heat you're using. All heat is not the same. And the goal of all of this is to get those molecules fully aligned. This slide, we're looking at amorphic material, amorphic PET like a preform, where these molecules all have a structure to them, but that it doesn't have a defined orientation. And it's showing the spherulites, the nucleuses that will form the growing of this heat-induced crystalline structure. Again, this is for hot fill. It's undesirable to have that type of crystalline structure in a preform or in the container. You can actually take a water or CSD bottle. If you're operating at too high a preform temperature, it'll become hazy. And that haze is a result of your growing crystalline structure, thermally induced crystalline structure throughout the container. And that's telling you you're way too hot. Within every container, you actually have three zones. There's the amorphic material, which would be the finish, and it would also be around the gate in the bottom of the container, where that material isn't really stretched at all. The overall sidewall and shoulder is highly oriented, where it's fully axially and radially oriented for getting your maximum mechanically induced crystalline structure. And then there's a transition zone, which is just below the support ring, where it's not quite fully oriented and it's not quite amorphic. And you'll also see that around that puddle of material that's around the gate in the base of the container. So this slide shows, it's a representation of the molecules in their amorphic state, in a semi-crystalline state, and then in the strain-induced crystalline state, where you have full orientation of the molecules. So this is another way to plot that, where on the horizontal axis we're looking at the deformation or stretching of the container, and on the vertical axis we're looking at stress. And within there, you'll see that the stress begins to increase pretty rapidly as you first begin to stretch it. It then kind of levels out, and then we'll hit a point called the natural stretch ratio, NSR. And at that point, you've hit the maximum strain hardening of that container, the maximum crystalline structure you're going to get. And literally, as you start pulling it, when the container stretches, it's like you hit a wall. It won't stretch any further. If you do proceed to stretch it further, that's where you start to get pearl. So when you get pearl in the feet of a container, you've overstretched it beyond that natural stretch ratio point. And you're actually starting to crack the molecules, and you're seeing light refracting off of those cracked molecules, which looks like pearl. And the reason this is really important to understand is as you're developing your bottle process, if you're not getting that material to that natural stretch ratio point, you won't have, if you look at it as a tow chain, you won't have chains that are nice and taut and in a straight line. You'll have them that are sagging. You've not fully stretched those molecules. You've not developed the maximum strain-induced crystalline structure. For things like a CSD bottle, what that means is once you fill it under pressure, it'll continue to grow. So things like labels that are popping off on the grocery store shelf, delayed breakage after the container's been filled, especially in a hot environment. That's because your process is very poorly set up. Typically, you have too much heat, you're not getting the proper type of heating, and you'll never be able to attain that the ideal orientation of those molecules. Preform temperature has a big effect on that also. I mentioned the proper heat. You want to have your lamp set up so you get the maximum infrared penetration into the preform wall. If you're running at very low output percentages, either overall output or in individual lamps, below 70%, you're not going to get infrared energy penetrating the wall of the preform. You're just baking it with heat. And if you have your preform temperature too hot, you get the same result. And what this slide's showing is blue is running the coldest preform temperature, where you're going to get the maximum strain, the maximum crystalline structure equals the maximum strength and performance of the container. If you take that material, the preform temperature hotter and hotter, the red line is the hottest, where you never get to the same level of strain-induced crystalline structure. Another byproduct of that is you're likely going to have a big puddle of material in the base and around the neck, And for CSD containers, that's the worst container you could make. You're going to get fatigue cracking in the base, and that's going to lead to a very weak container and often delayed breakage as it's being transported to the grocery store. So looking at the type of heat and the actual preform temperature you're using are critical in the development of your process to attain the maximum performance of that container. Another factor which comes into play is, which can vary your process dramatically, is how much moisture those preforms have absorbed. From the time the preforms come out of the injection press, they're absorbing moisture. At the time they come out of the mold, they have an extremely low content of moisture, typically less than 100 parts per million. As they sit, once they've been made, PET is hygroscopic, which means it'll absorb moisture from the air. Depending upon the humidity, the time, humidity, and temperature that preform's been subject to will determine what degree of moisture is absorbed. So what this slide is showing, at a 3-month interval following production of the preforms, the bottom white squares are in a very low humidity environment. So something like the Arizona desert, producing bottles in Phoenix, where the relative humidity is 5%, and even out at 3 months, they're only sitting at about 100 parts per million moisture. Whereas if you're in a hot, humid environment, at 3 months, you're pushing 2,000 parts per million moisture. That makes a tremendous difference in what's going to happen in that blow molder and the process. As you're getting up to that level of moisture, you're going to have to decrease your preform temperature 5 to 6 degrees centigrade to make the same container. So if you have preforms that are in your warehouse, ones that you just got in, they're a week old, and ones that have been sitting there for 3 months, and you're sitting in South Carolina in the summertime with very high humidity, when you intermix those, you're going to be wondering what's going on downstream in your line, because it's going to be running terribly. And it's all a result of that hugely changes the process of the container. So that's something you need to be aware of in the overall PET bottle production process. I mentioned heat. This slide shows that the same humidity, 75% humidity, over the course of about 2 weeks, it's showing you the absorption rate at basically room temperature, 23 degrees C versus 35 degrees C, which is pushing 100 degrees Fahrenheit, versus 45, which is 110. So if you're in Asia, this slide applies directly to you, because what do they have? Very high humidity, very high temperature. That means it's going to absorb a lot more moisture in a very short period of time, which again can dramatically affect the bottle process, which will affect how the containers run through the labeler, the filler, the capper, the bundler, and you'll be looking to find out what's wrong with my labeler when it's really what's wrong with your bottles. One of the last effects that has is, as you start absorbing more moisture, it affects the IV, the intrinsic viscosity. We mentioned that there's different levels that you want depending upon the container. Well, it can change it so dramatically that you have IV of 0.8284 for a CSD container, and after 6 months, when it's been sitting there absorbing moisture, you now basically have the IV that's suitable for a water bottle. So that container is not going to perform nearly as well. You're going to have base blowouts when you're producing the container and wondering what's wrong. With that, that's a brief introduction to our PET101. The slides that are coming will show you a layout of what other topics we cover in there, which covers from the material science through injection press, drying the resin, the blow mold process, and the quality control function. If you want further information, please go to our website, agrintl.com. Thank you very much.